I recommend you become familiar with the dynamics of these four common scenarios, in all of which mass cancels out while analyzing Newton's second law, resulting in an acceleration that does not depend on the mass of the object at all. Number one, free fall. An object is in free fall if the only force acting on it is the force of gravity. And so when stating Newton's second law here and combining that with Newton's law of gravity, we get the cancellation that will recur in the next three scenarios as well. What we have here in Newton's second law is mass appearing in this denominator representing the resistance of the object to any acceleration. This mass represents the inertia of the object. It's sometimes called the inertial mass. In Newton's law of gravity, mass also appears here, but it's performing a very different function. This property of the object, this mass, determines how strongly the object feels the force of gravity, and also how strongly it exerts gravitational forces on other objects. So for that reason, this quantity is sometimes called the gravitational mass. And so it's one of the great curiosities in nature that these two properties of any object happen to have exactly the same value. This property that resists acceleration and this property that exerts gravitational forces, they happen to be the same thing. And so when we set up Newton's second law here and end up with our force of gravity divided by the mass of the object, this quantity, gravitational mass, and this quantity, inertial mass, they happen to be the same thing. And so they cancel out, resulting in this acceleration for any object in free fall regardless of the mass of the object. Scenario 2, a frictionless ramp. Okay, so this is a two-dimensional scenario. It'll be a little bit more involved. I'll mention our strategy for dynamics. We always start with a careful analysis of our free body diagram. And then step 2, AAA, we align our axes with the acceleration. This is where we identify which direction the object is going to accelerate, lay down our axes, sometimes tilt them, sometimes bend them, and then break up any forces we have in our FBD that don't align up with our axes into components. Then step 3, where we set up Newton's second law. And if we're in more than one dimension, we need N2L for each dimension. So an N2L for the x direction and N2L for the y direction. Here on our frictionless ramp, we'll have force of gravity and a normal force. Since the box will be accelerating up or down the ramp, we tilt our axes to align with that acceleration. I'll choose the x direction to be pointing up the ramp. And so that's step 1, FBD, step 2, AAA, but part of step 2 is identifying any forces that don't align with our axes, namely the force of gravity here. So we'll have to break up the force of gravity into components. Make the force the hypotenuse of a right triangle with one leg parallel to the y-axis, one leg parallel to the x-axis. And then do a bit of geometry here. If this angle down there is theta, then by analyzing our opposite angles, our interior angles, and our complementary angles, we determine that if this angle here is theta, it's congruent to this angle up here, which would be this angle right there. So that is also theta. Okay, that's all part of step 2, AAA. Now, set up Newton's second law. Once for each direction, the y direction and the x direction. So you should always have on your page a statement of N2L. That's you stating your equation, then showing the terms in the sum of forces in your numerator there. In the y direction, the forces cancel out. In the x direction, state N2L, show your terms in the numerator, expand that to indicate that we have to do the trigonometry. We want this component right here, FG sine theta. FG can be replaced with mg. And at this point, we get the same cancellation that occurred in the free fall problem up above. Mass cancels mass, so we see this result. Any object on a frictionless ramp, whether it's velocity is up the ramp or down the ramp, its acceleration will always be down the ramp and have exactly this value, g sine theta. Does not depend on the mass of the object, just depends on the angle of the ramp here. So compare. In free fall, your acceleration is guaranteed to be little g. On a frictionless ramp, guaranteed to be g sine theta, regardless of mass. It's a result that I recommend you memorize for quick use, but also be able to quickly rederive using these steps. Scenario 4, sliding with friction. Suppose we've got an object sliding along a horizontal surface and friction is bringing it to rest, slowing it down, bringing it to rest. It'll be kinetic friction then, since there is slippage between the two surfaces. If they're slipping relative to each other, it's kinetic friction. Here's our free body diagram. So that's step 1 of our 3-step process. FBD, now AAA. We'll have normal XY axes. Our acceleration will be to the left because of that force of kinetic friction there. And now Newton's second law, once for the x direction, once for the y direction. State your equation, show the sum of terms, reach this conclusion here about the normal force and force of gravity being equal. Restate N2L. Now here, for handling that force of kinetic friction, you also need to always state the equation that we use to calculate the value of kinetic friction. That'll be the coefficient of kinetic friction, mu k, times the normal force, the contact force between that object and the surface with which it is experiencing friction. So state this equation on the page before you plug it in there. Fn, we've shown, is equal to mg. So here's where that substitution comes into play, and that gets us here. Negative mu k mg over m, and once again, we get that cancellation of mass, resulting in this simple expression for the acceleration of our object as it slows down, independent of mass. Any object sliding along this surface will have this acceleration, depending only on the composition of the materials, that is, dependent only on the coefficient of kinetic friction right here. So it doesn't depend how massive the object is, it depends on what it's made of. What it's made of completely determines what the acceleration is going to be. Oh, and once again, I recommend you memorize this result, the standard result for the acceleration of an object sliding with friction, but also be able to quickly rederive it by showing these steps. Last one. A mass that's accelerated by a moving surface, like a box sitting on a flat truck bed as the truck accelerates forward, and friction pulls the block along with the truck. We want them to move without slipping, so it'll be static friction, if there's no slippage, static friction that drags the top block along with the surface as the surface slides to the right. Static friction preventing the surface from sliding out from underneath the box. So this box is accelerated forward by static friction. Similarly, if you're carrying a tray and you've got something sitting on that tray, well, your hand is not directly touching that box. Your hand is not pushing it forward. It's static friction between the box and the tray, the moving surface, that is accelerating that box forward. So in either of these situations, the max acceleration that we can achieve will occur if static friction is maxed out. We know static friction can be stronger than kinetic friction. Its max value will be greater than the value of kinetic friction. And so we get max acceleration if we're not slipping. So static friction and static friction is at its max value. Here's our FBD. Step 1, FBD. There's static friction that'll be accelerating the box forward. There's our axes, nothing to break up into components. And so, once again, we state Newton's second law in the y direction, show your balance of forces in the y direction, restate in the x direction, and then off to the side, have this statement where you indicate how we are going to calculate a value for static friction. We want static friction to be maxed out as strong as possible, and this is the expression for the maximum value of static friction, mu s times the normal force. State that, then show it plugged in here. The mg can get plugged in to get to the next step where mass and mass cancel once more, leaving us with this handy expression for the maximum acceleration that you can achieve with static friction. Doesn't depend on the mass of your object here, doesn't depend on the mass, that cancels out. All it depends on is what the mass is made of and what the surface is made of. The combination of surfaces determines some specific value of the coefficient of static friction here. So compare that, mu sg, to our result from scenario 4. Mu kg, that's the acceleration we're going to get. This fraction of g is the acceleration we're going to get as this box slows down. And mu s, which is some number less than 1 usually, will give us this fraction of g is the max acceleration that we can give to this object on our tray. Now, this FBD also applies to these scenarios. Say a sprinter pushing off of a surface running to the right, or a bicycle tire or a car tire pushing off of the surface as the bike accelerates to the right. Static friction we can also think of as traction. This is your traction. So whether the surface is pushing the object to the right or the object is pushing off of the surface, if there's no slippage between the two surfaces, it'll be static friction causing the acceleration. And so this FBD right here would be the correct one for either of these two scenarios as well. So this calculation also gives us the maximum acceleration that your sprinter can achieve pushing off of the ground, or that your bicycle or your car can achieve as its tire is pushing off of the ground using that static friction, no slip. So this is your personal maximum acceleration when you are running. It does not depend on your mass, it doesn't depend on the mass of the bike, on the car. Your acceleration is entirely dependent upon that coefficient of static friction right there. So all that matters is the material that the bottom of your shoe or the bottom of your tire is made of. It's the material that determines how much traction you're going to get. The material determines mu. The material determines what fraction of g is the maximum acceleration that you can achieve. Once again, I recommend you memorize this result and also know how to quickly rederive it if necessary, showing those steps.